To connect a rider with a driver, a ride-sharing platform evaluates a chaotic, constantly moving map, identify an available car within a 2-kilometer radius, and lock in the match in less than 50 milliseconds. The most obvious way to solve this is brute force. The system takes the rider's exact GPS coordinates and mathematically calculates the distance to every single active driver currently on the map. Computing the exact trigonometric distance between 2 points requires heavy floating point arithmetic. If the application has 1 million active drivers, the database has to perform that complex calculation 1 million times, just to satisfy one rider's request. Now multiply that by thousands of requests coming in every single second. You cannot solve a math bottleneck of this magnitude by simply adding more RAM or faster CPUs to a server. Surviving this requires abandoning standard database structures entirely and rethinking how a database indexes information. At a global scale, traditional relational database architecture collapses under the weight of geographical processing. Geographic data is unique because it forces a system to evaluate 2 independent variables at the exact same time, longitude and latitude. This animation shows what happens when a standard SQL query attempts to filter on 2 spatial axes simultaneously. Because traditional indexes read sequentially, the database cannot skip ahead. It initiates a full table scan, iterating point by point through every coordinate in the system. Evaluating millions of irrelevant locations one by one instantly floods the server's memory buffer. The CPU load spikes straight to 100 heat. This chart plots the algorithmic failure in real time. This is O of n, or linear time complexity. As the number of drivers on the platform grows, the time it takes to execute a query scales linearly right alongside it. It is mathematically unsustainable. Treating physical, multi-dimensional space as a list of simple alphanumeric rows ignores the multi-dimensional nature of geography, and it guarantees system failure. To understand why relational databases fail here, we have to look at the B-tree index, the highly efficient sorting structure that powers 99% of traditional databases. This diagram illustrates a standard B-tree. It excels at taking a single variable, like longitude, and cleanly sorting it into branching leaf nodes to guarantee rapid logarithmic lookups. But there is a critical flaw. By indexing the longitude axis, the latitude axis is left completely unsorted and chaotic. When an application queries both dimensions, the database has to pull all the matching longitudes into active memory and then manually filter that massive data dump against the unindexed latitude values. That secondary manual filter negates the speed benefits of having an index in the first place. The solution is to use a spatial database. This is an engine explicitly optimized for multi-dimensional vector models, objects like points, line strings, and polygons. Processing a 2-dimensional grid requires a structural index that natively understands bounding geometry, not just alphabetical or numerical order. That multi-dimensional structure is called the R-tree, or rectangle tree. Here is how it works. Instead of attempting to sort individual coordinate points, the R-tree encapsulates geographic clusters into nested geometric blocks. These boundaries are known as minimum bounding boxes. The system draws the tightest possible rectangular perimeter around the outermost nodes of a given data cluster. In this hierarchy, the root node of the tree represents the largest bounding box covering the entire region. The child and leaf nodes represent the progressively smaller, tightly packed boxes nested inside it. When a writer requests a car, the database engine simply checks if their search radius geometrically intersects with a parent bounding box. If the search radius falls entirely outside a box, the database instantly discards every single data point inside that box. Compare this multidimensional logarithmic lookup to the sequential scan of a standard SQL database. The R-tree allows the database engine to confidently ignore 99% of the geographical data on the map without ever executing a single complex distance calculation. The R-tree scales because it treats coordinate elimination as its primary function, purging vast territories of irrelevant data in a single step. In a production environment, developers query an R-tree using PostGIS, a spatial extension built for Postgres databases. It operates on a hyper-efficient 2-stage spatial query that separates rough filtering from precision math. Look at this snippet. The first stage converts raw GPS float values into a unified spatial geometry object using the st makePoint function, allowing the database engine to actually read the location. Next comes the bounding box filter, std-within. std-within hits the R tree's bounding boxes to rapidly reduce the search space from thousands of drivers down to a micro-subset located within a rough 2,000-meter block. Finally, the code executes the precision step using the stdistance function on the remaining filtered results. stdistance requires heavy, CPU-intensive trigonometric math. That is exactly why it is strictly reserved only for the micro-subset of drivers that already pass the bounding box filter. The spatial database sorts the final output of stdistance by proximity and returns the single closest driver ID to the user. Standardizing raw coordinates into vectors and layering a cheap bounding box filter before executing expensive precision math is the exact mechanism that makes sub-50 millisecond routing possible. But there is one major architectural vulnerability: mobile network latency and intermittent cellular connectivity. Relying solely on a centralized spatial database results in complete data failure if a driver loses connection in a tunnel or a rural area. The solution to this vulnerability relies on edge computing, specifically the deployment of an embedded mobile database like SQLite or Realm. A mobile database is a lightweight, serverless engine that runs entirely within the localized memory constraints of the driver's smartphone. It allows the driver's application to log coordinate changes, read configurations, and write states locally, with zero network latency, even when completely offline. Once cellular connectivity is restored, a synchronization communication gateway batches the data packets and automatically resolves any update conflicts with the master spatial database. This architecture provides consistent vehicle tracking through asynchronous background syncing between the mobile client and the central server. Let's trace the complete lifecycle of that 2-kilometer radius ping generated by a writer. The driver's location data originates in their local mobile database, syncs through the gateway, and streams straight into the master spatial database. The R tree immediately intercepts the query, deploying nested bounding boxes to filter the map and bypass the scanning nightmare. This data pipeline balances the limitations of mobile hardware against the geometric logic of the R tree to maintain sub-second performance. Global scale is achieved when software architecture is engineered to respect the geometric constraints of the data it handles.